All righty. Welcome back for another week of fun. We are going to finish up chapter 3, do just one section of chapter 4, which means we're not going to talk about projectile motion. And then we're going to get into chapter 5 talking about fluids. So it's going to be covering a few chapters, just pieces of each. Finishing up chapter 3 with energy sources. Energy is an important thing that we talk about in our society. That's why I prioritized putting the sources of energy here. Where do we get energy from that we use daily? We talked about the sun being a primary source, but we use electricity that comes from the wind. What did you say?
Water.
Okay, water.
Logs.
Okay, biomass.
Sorry, y'all. Someone else answer.
And
Where do
energy.
you get energy from besides biomass, water, the sun?
Food. Wait,
And
what?
rain.
Energy?
Yeah.
Food.
Fossil
Okay,
fuels?
food, fossil fuels. Okay, that's a pretty good list.
Reactions of other things hitting us.
Reactions to other things hitting us. What is that?
Yeah, if two cars, if you turn them in, one car transfers them to the other car, thus that car has energy.
That is true. That's not energy that we use per se. It's energy we interact with.
You can use it.
This is an important topic. We could, yes, I suppose. This is an important topic because we have things like, well, the USA today is the largest producer of oil. Did you know that?
Yeah, now.
Do now.
It still is?
It is. The USA, for most of my life, we had a very simple policy with oil. Let's not use ours. Let's use other people's. With the idea, I think, being that oil is a non-renewable energy source. That is, oil, once you've used it all, it's gone. It's generated so slowly that you're going to be out of it. And so if we save ours, then when other countries are out of oil, we'll be the only ones with oil. Under the last few presidencies, the philosophy has changed somewhat. So now we are extracting huge amounts of oil of our own. How do we extract that oil?
Fracking.
Okay, fracking is the thing that has really helped us in extracting a lot of our oil. Do you guys know what fracking is?
Where you shove water like underground base, kind of that.
Isn't it like where you move the tectonic plates?
Oh, no.
Okay. Well, no.
that would be a scary thing. Although,
And you talk wild nonsense.
we talk loud nonsense. That's apparently fracking. Okay, so Alex appears to know what she's talking about.
Yeah, the rest of us don't.
You have oil in rock. If you've ever done anything like go to Fossil Butte and dig around for fossils, one of the things you notice, it smells oily.
Fossil fuel?
Yeah, it's in Wyoming. It's a national park. The fossils smell oily, and that's because oil was created when the fossils were crushed. And you have to have the right environment to create the oil. It's not like everything that dies creates oil. But you have this rock that has lots of oil in very small amounts all over the place. Yes.
I was just gonna ask, have you ever been to like where they actually extract the oil?
I have not.
Me neither.
But they'll have what they call fossil shale rock that has lots of oil in it. And so the idea of fracking is very similar to this picture I have here for geothermal. This is a special kind of geothermal, but they pump water into the rock, and then that water causes the rock to fracture. That's the fracking. And then the fractured water, they can extract, or the fractured rock, they can extract the oil from. Now, Josie mentioned moving tectonic plates. Earthquakes are the result of tectonic plates sliding against each other. Something we will learn later when we get to earth science as part of physical science. And one of the concerns about fracking is as you're breaking up the rock down there, you can cause slipping, you can cause stresses between plates and cause slipping, i.e. cause earthquakes. And so a concern about fracking is you're potentially causing earthquakes. Another concern is we have groundwater, another topic we'll learn about when we get to earth science. And with the fracking, you're fracturing rock, you're going to allow water then to seep through, and so you can have contamination of your groundwater. So those are some concerns about fracking, but we're doing a lot of it, we're extracting a lot of oil, and you know what that does for us? Makes our gas prices much lower. You might remember that, well, you might not too, that about 6 years ago or so, oil or gas prices were more than $4 a gallon here. And still are in
My
California.
time it was $7.55 a gallon.
And now it's not so much because we're producing a lot. Questions in here?
In lab,
Yes.
when you were talking about if we needed help with the homework, you needed some extra eye contact with Vanessa and I. So I've been checking every single day if you put in homework too and you still haven't. I'm really starting to stress.
Oh, you're talking about grading.
Yeah.
Okay, yeah, I was doing great yesterday and I didn't get it done. There was this football game to watch instead.
You just really were looking at us, and I really felt like you were trying to say that we did bad.
No, I did not. I haven't graded. I was not at all making such a duplication.
There's just two sides to the ring, you know?
Yeah, I'm sorry about that. I have not looked at it, so I don't have any
You
such.
were right there, and like looking, and I was like, looking.
Oh, you're
try-
probably curious to what
I
you're
try to make eye contact with my students.
I
you know?
just felt really targeted.
I am sorry. It felt hard. Sorry about that.
It's okay.
Okay, so other sources for energy, ones that are renewable are ones that we like to focus on because if we run out of oil, we want to have something we can use to, power our computers. And so besides oil, we have this here, which, as I said, the picture works for talking about fracking. This is dry rock geothermal power. Geothermal power is using the energy stored as heat in the earth. And I say stored as heat. Heat is a transfer process, so it's thermal energy. You can't really store heat. But you have hot rock down there. And so in places where you have water in the hot rock, you have geysers. And that can be used. So in Calistoga, California, right close to PC, they have a geyser power plant. I took my students there on a field trip. So I have been to there. That's just natural geysers. Here it's artificial geysers. They drill a hole down to a place where you have hot rock, and then they put water in, and the water causes the rock to fracture, creating a cavity, and then they fill the cavity up with water. That water gets hot, and the hot water then expands and they use it to drive steam plants.
Does water boil down there? I'm just curious.
The answer is kind of a qualified yes. When you have higher pressure, it doesn't boil, and it boils at a higher temperature, at higher pressure. And so something like a geyser, the reason the geyser is not constantly going off is because you build kind of a pressure cap in there, so the pressure builds without it boiling, and then when it boils, that's when it erupts. So that's my qualified answer. In this case, it heats it to a potentially boiling temperature, but they probably keep the pressure on so it doesn't actually boil until they let it out.
Right.
I noticed the probably there because I don't have actual experience with this. Another one is solar power. In our house in Colorado, Amy and I want to put up solar panels because we get a lot of sunshine. We're at 9,400 feet elevation, so there's less atmosphere to block the sunlight. And so we have these little photovoltaic cells, things that when you shine light on them, they produce electricity. You could also have hydroelectric turbines. That is water that pushes a turbine. How is that listed under solar power? I talked about last class period. You have the hydrologic cycle that includes water being heated by the sun, evaporating into the sky, falling elsewhere, like at high elevations, and then you can use the energy there. Wind turbines. Wind is created a lot around here, even more at our house in Colorado, because places where you have high temperatures and low temperatures, you tend to have high pressures where it's high temperature, low temperature pressure where it's low temperature. And as we'll learn later today, that will cause air to flow from the high pressure region to the low pressure region. So you put up your wind turbine to capture the kinetic energy of that moving air. And then bio-based fuels, that's biomass, like you said, burning logs. Alex?
What is wind pollution? And is that an actual thing or is that propaganda? Because I just Googled it and nothing came up.
Well, President Trump made some ridiculous statements about wind power.
Yeah.
But wind, nothing is without problems. You know, for instance, your photovoltaic cells are going to cause some hot surfaces probably that could damage animals that touch them. Hydroelectric turbines, those are going to require you to dam up something which then is going to impact the water temperatures, the water flow rates, so it changes the habitats. Wind turbines, they make noise which drives some animals away. Surprisingly enough, plenty of birds go through the blades and get chopped up. So there are, nothing is without hazard. And there's some noise with the wind turbines that people get annoyed with as well as the animals.
It's actually not that bad. I've lived directly under one.
So you have some experience there that I don't. But
Yeah.
those are some of the drawbacks that people will point to.
Mhm.
And so everybody, you've got to make decisions about what's acceptable. I personally really like hydroelectric power because you've got all this water at a high elevation. Yes, you have to dam something up, but you then take the energy from it, and then the water goes on and can be used for irrigation or drinking. Yeah, it makes good sense to me. But then, fish, their spawning pond is up there and they can't make it because you dammed it up. Fish ladder,
I can't swim that high.
still water stops their spawning impulse, so they will just stop and hang out in still water instead of going up to spawn. So there are downsides, I have to admit, to the thing I like. I also like nuclear power as an option. The problem with nuclear power, what's the problem with nuclear power plants? What do you think?
Well, there's a lot
Gas
of waste and we can't get rid of it right now.
Okay, the radioactive waste, I'm not sure what you're talking about.
I don't know either.
Are you talking about the clouds that go up into the air?
Maybe.
Nuclear power plants are self-contained, if you will. They're isolated. So you have virtually no radioactive contamination with anything unless there's an accident.
I was gonna say, aren't they just a big factor in fear of them is just them combusting? And
Well, there's no combustion in a nuclear power plant. Combustion is burning, and nuclear power
I guess
plants,
it wouldn't burn, they just explode.
they shouldn't.
Oh, okay.
But there have been disasters. There have been two primary disasters. There was the Chernobyl disaster, where they, as I was told at least, they were checking to see how quickly they could recover if they allowed it to overheat. And
They were down.
they weren't able to. And it got really hot water expands and blew the top off, and then they had radioactive material that went up into the atmosphere, and that causes a lot of damage. Most nuclear power plants, they're very isolated, so there's far less radioactive exposure than you get from a coal burning power plant. Most people don't think of coal as radioactive, but that's where we get our radioactive stuff, is for digging it up out of the earth, and coal is something we dig out of the earth. It's got radioactive things in it. And when you burn that, you're releasing those radioactive elements into the atmosphere. And so if you're worried about radioactive pollution, coal power is a much bigger concern than nuclear power. I point out coal because it's a rock we dig up, as opposed to oil, which is going to be refined and probably a much cleaner process in terms of radioactivity.
Do we still dig up quite a bit of coal, or I thought we had closed almost all of the coal mines?
You still see plenty of trains that are carrying nothing but coal. So I don't know, I'm sure it's a lot less than it used to be. Of course, under President Trump's policies, one of his policies that I personally am not a fan of is his environmental policy. President Trump has a basic premise of business first.
Mhm.
And so relaxing a lot of our environmental protections. And I think we need those. And so coal, I think, is making a rebound under President Trump's administration because of his policies regarding pollution.
Is it pretty cheap to mine coal? Compared
Only
to
if
drilling
people
for
are
oil?
disposable.
I don't know. I mean, everything I see is things like, watching Bonanza and all these people dying in mining, not silver mining, but
I was
No, I
curious,
think it
compared
is
to
dangerous.
drilling oil, which one's cheaper?
I think of it as dangerous. To me, dangerous corresponds with very expensive, but I don't know.
Okay.
Of course, these days, I think what they do is they just, chew down a mountain rather than dig holes.
Jig holes, yeah.
But what do I know? I don't know a lot there. There are some other energy things that we don't talk about as much. Electricity comes almost always from boiling water. If you have a nuclear power plant, it's because you're boiling water that you're creating electricity. You have a coal or an oil power plant, you're boiling water. A biomass power plant, boiling water. So boiling water is a big thing for how we go from one type of energy to another. Synthetic fuels, things that are man-made, like we can make, we use ethanol that comes from corn, I talked about. There are also ideas of using algae to create a biodiesel that have a lot of promise. Hydrogen, it's not a source, but you can generate from multiple sources, like from water, and use it in fuel cells or internal combustion engines. So here's how you can create free hydrogen. You take a battery and you put two probes in water, one connected to the positive side, one connected to the other side, and the process of electrolysis will separate hydrogen and oxygen. If you combine hydrogen and oxygen and give it a little heat, they'll burn and release thermal energy. And so it's something you can use for energy, but the thing is, and you always have to remember this, we can't create or destroy energy. So in separating the hydrogen, oxygen, and water, we have to put energy in. When they burn, they're going to release energy, but they're not going to release more energy than was required to separate them. So it's not really a good source for energy because it's just storage. Sunlight is a really good source because despite what some politicians may have said in the past, you cannot use up the solar energy by having solar panels. This solar energy is striking the earth everywhere, anytime it's daytime. I almost said everywhere all the time, but of course when it's nighttime, it's not. And that solar energy, some of it is absorbed, some of it is reflected. Yes, you are absorbing more of it, but a lot of that absorbed energy you're converting into electricity, and it really has very little downsides, which is why I want to use it. That's why energy sources talk. Why did I talk about this? Because it's a hot topic. It's something that you're going to probably want to talk to your fourth graders about when you're doing science. Energy, why is it important? Why are mom and dad worried about it? Why is President Trump making it so much more available? Why is President Trump relaxing environmental restrictions to allow energy to be more available? What is his end goal?
Money.
Money drives almost everything.
I was gonna say, is that every politician's end goal?
Yeah, it
Unless
is.
you're in the Green Party?
He's really shafting the world to get it though. That's the difference.
He wants American businesses to be able to produce things at lower cost, and making energy cheaper is a big way. Making it so they don't have to worry as much about their pollution is another big way of allowing them to do stuff cheaper.
And he wants bail.
It's what?
And he wants bail. Bail. And he wants bail, like funders.
I'm still missing the point.
He's trying to make friends for when.
Oh. Yes. By the way, the vote on Senate's trial was postponed until later today.
Mhm.
Primarily, I think, so the Democratic senators who are running for president, there are 3 of them, to leave Washington and get to Iowa for the Iowa caucuses. Okay, so on Wednesday, they will have the final vote and a debacle, no matter which side you're on, you have to do this debacle, will be completed. You guys have heard about
So to let
Newton
everyone know.
and his apple? Have you heard about Newton and his apple? I guess. What?
We've talked about his apple in here before, haven't we?
I don't think so.
Yeah, we have actually.
We have. What
And we were
important
talking
thing?
about gravity.
Okay, yes, because that is the point. This is my lead into gravity again. What's the important point that you can tell your kids when you're teaching school about Newton's apple?
It's gravity.
Okay, it has to do with gravity, but what?
Everything happens for a reason.
That's a truism, but that's not the. Well,
Oh,
here,
you need to test something before you consider it to be fact.
that's also a good thing. I mean, that's one of the important things I want you guys to get. But here's the basics of what was believed before Newton and his mythical, I say mythical, it could be since apple. Basically, if I want to put a force on Jessica, I have to touch her. I can't go and put a force on her. I have to actually make physical contact, which I didn't do. So Newton, as the story goes, was sitting under the tree, an apple fell on his head. And he said, why did the apple fall? Well, according to Newton's second law, for it to change its motion, well, its first law, to change its motion, there has to be an unbalanced force. The second law is what gives you the acceleration as a result of that unbalanced force. Third one. And so he said there had to have been a force acting on the apple to make it fall and hit me on the head. But that means that there was a force on the apple when nothing was touching it. But not magic, because science starts with a premise that there can be no non-natural events, no magic, no miracles. So science pretty much starts with the premise that God can't act. Every explanation science comes up with is something that is based on a natural thing. And so he said there has to be something that was acting on that from a distance. And that's what was revolutionary. That's the whole point of Newton's apple story, is that a force can act at a distance. And so then through experimentation, Sir Isaac Newton further discovered that that force, well, I should go to this first. The next thing he went to from the apple was, why doesn't the moon fall? Because if there's a force acting at a distance, the moon is out there at a distance, and the moon should fall down and hit the earth. Does that make logical sense to you? If an apple falls from a tree and hits you on the head, shouldn't the moon fall from the sky and hit you on the head too?
Yes.
If there's no gravity working, then yeah.
Well, no, because of gravity. Not if there's no, but because of it should. And his answer that he came up with, and of course I just use balls to illustrate his point. If I take this ball and I slowly roll it off the table, what's it going to do when it leaves the table?
Fall down.
How far from the table?
Whatever the top of the table is to the bottom.
What do you mean? What do you ask?
Well, how far horizontally did that fall from the edge of the table?
Oh, like a couple of inches?
A couple of inches. Now, if I have it going fast, what's going to happen?
Well, it's gonna go about that far out.
About that far out. It's much farther out, right? So he said, okay, now if that ball is going super fast, then it's still going to fall because of gravity. But it's going to travel horizontally a much bigger distance. But the thing is, it's been known since a couple hundred years before the time of Christ that the earth is a ball. And if the earth is a ball, that means that the earth is sloping away as you move sideways. And so the moon is going fast enough that it's falling, but the earth is curving away, so it just keeps falling and goes in a circle and never gets closer. So the moon is indeed being pulled by gravity, but it doesn't fall down because of its horizontal motion. So this picture here is illustrating that if there was no gravity, the moon would stay in constant motion, constant velocity, and we'd say bye-bye. But because of gravity, it keeps falling toward the Earth and ends up doing pretty close to a circle around the Earth. Now, just something really fun to know.
Fun fact.
Yeah, fun fact with Dr. Webb. Lots of them. We talked about tides before in the homework problem. Tides are the result of the gravitational pull between the Earth and the moon. So, stuff that is closer, according to my next slide here, the force of gravity, Newton just determined, is proportional to the masses and inversely proportional to the separation squared. So if we look at this picture, D is the separation between the two objects. So this, from center to center, is D. So that line there is D. And then mass 1 might be the mass of the moon. Mass 2 is the mass of the Earth. And force gravity is G times mass 1, mass 2, divided by the separation squared. So not only is the gravity of the Earth acting on the moon, but as Newton's third law for opposite reaction says, the moon is acting on the Earth. The moon is pulling up on the Earth. And so the parts of the Earth that are closer to the moon, D is smaller, right? Parts that are farther from the moon, D is bigger. But what happens to the strength of the force if D gets smaller?
The tides come in.
So here's a smaller D. If D is smaller, what happens to this force? If I divide by, let's say, if I divide by 1 squared instead of 2 squared. Yes, as D gets smaller, the force gets bigger. And so the force on the material that's closer to the moon is stronger per unit mass, per piece of, per molecule, let's say. And what that causes is water, which is easy to flow, gets pulled up toward the moon here. So we'll have a higher tide on the side of the Earth closer to the moon. But what about the distance that's farther? So this here, this distance here, going to the far side. If that's a larger distance, what does that do to the force?
The tide's gonna be out more.
The tide will be out more, but what is it doing to the gravitational force if you have a larger separation?
Well, it's not as strong.
It's not as strong. And so because it's not as strong, the water is not changing direction as much as the Earth does, so it bulges out like that. So you have a high tide on the side of the Earth that's closest to the moon and a high tide on the side that's farthest from the moon. Because gravity is stronger for the closer part, weaker for the farther part. But then there's the crazy thing, the fun fact. The Earth is rotating. So the Earth is spinning, and as the Earth spins, do you remember when I talked about the air in the Earth is being pulled with the Earth due to friction? So the Earth, we don't feel a breeze from the Earth rotating because the air is rotating with us. Well, the water is going to do the same thing. So this high tide is going to rotate with the rotation of the Earth. But what that does is it creates high tides that are a little bit ahead of the moon because of the Earth pulling it forward. Now, what's crazy about this? If it's a little ahead of the moon, that high tide actually is tugging the moon forward.
So that's what's pulling the
So
circle.
the moon would go in a circle on its own just due to gravity and its motion. But if you're pulling on it in the direction it's moving, what's going to happen? It's quickening, speeding up. And so the moon is slowly speeding up. And the Earth, of course, its rotation is slowly slowing down. But if it speeds up, what does that do to kinetic energy? Increases it. So the moon is gaining kinetic energy. As it gains kinetic energy, as it's going faster, it's going to go farther before it falls, right? And so the moon is slowly moving away from the Earth by something like a 1/4 inch a year. So it's not a huge amount, but the moon is slowly moving away from the Earth.
Aren't we technically doing that with the sun as well?
I don't know how, there should be a similar effect, but it would be really, really weak. So technically, probably yes.
I'm gonna run this over with you so I can full understanding. High tide at New Smyrna Beach is between 10 and 11 a.m. So at 10 and 11 a.m., the beach is either closest that it's gonna get to the moon or farthest that it's gonna get from the moon.
It varies from every day. High tide is a different time every day because high tide, if we ignored the Earth's rotation, high tide would be at the moment either the moon is closest to overhead or closest to the opposite side of the Earth. But because of the Earth's rotation, high tide is going to come a little before that. So every day it's a little different because it takes, 27 and a half days or something like that for the moon to go through its phases, 29 or something for it to do it's 27 and a half or so to do a complete rotation, 29 or so to go through the phases. Anyway. So we have tides because of this gravity, but an interesting fact is because of the Earth's rotation, it's making the moon move away. Okay, so now I'll skip past this and go to our question. I didn't put the thing to sign up for WooClap in my presentation, so I'm going to have you just answer because it'll take too long for us to otherwise do it. So there's a gravitational attraction between you and everyone else in this classroom. With whom do you have the strongest force of gravitational attraction? Is it me because I'm more massive than all the rest of you? Or is it the person sitting next to you because they are the closest person to you? Or is it the same for all of us?
I feel like it's the same because there's also not too much of a difference between you and I in size, like enough to cause gravity.
You are either being very negative about yourself or very generous to me. I am sure I outweigh you by a lot.
Well, no, I feel like it's genuinely a part of physics. Like, the grand scheme, we're not different in size. Not too different, at least.
So do you think you and your soulmate have a slightly more gravitational pull?
No.
I do.
Okay, but being serious. I wrote in black the equation. Alex has given us her answer and her reasoning. What about the rest of you?
I would say B or C, probably C.
I want to be like,
It's definitely not A.
Okay, so
I'm going with C.
Jessica simply says, Alex is wrong, I don't know what's right.
Thanks, Jessica.
You said
Yeah.
C.
Oh, did she say C?
Yeah, I agree with her.
Okay.
She didn't
My
say
bad. I
She's
misremembered.
trying to start problems.
And what did you say?
I said C and then shrugged my shoulders like, well, I don't know, but I'm going to just give an answer and hope it's right.
Okay. Well, let's look at the facts. Force of gravity is G m1 m2 over d squared. Which is more important, the m's or the d's? The d because it's squared. So that's more important, but they both are important overall.
So it will be
Now-
B.
The answer actually is because all of you are reasonably close to the same mass, which is what Jessica was saying, but the distances between you and other people tend to vary quite a bit, and because D is already a bigger factor. If you look at the separation between Annabelle and Josie, it's about a meter. Between Jessica and Vanessa, it's a little less than a meter. And even Alex and the two ladies in front of her, they're similar distances to her, but much closer than to the other two ladies, and much closer than to me. So the force of gravity is going to be strongest to those that are closest to you unless you have a really big mass disparity. So for instance, the force of the gravity of the Earth on me is much smaller than the force of gravity of the Earth on the moon, even though the moon is very far away compared to me. The moon is about 5 times farther from the Earth than I am from the center of the Earth. But the mass of the moon is much more than 5 times my mass, much more than 25 times my mass. And so the force of the Earth on the moon is much bigger than the force of the Earth on me because of the mass disparity. What direction is the force of gravity? I did not say this, and I need to.
Up, down, and sideways. No, just down and sideways, correct?
Well, the answer is actually a very simple one-word answer.
Oh, so it's just down.
It's attractive.
Oh, wow.
It's attractive. I had it in the words up there, attraction between you and everyone else, but I didn't specify it. Gravitational force is always attractive. It's always pulling things together. So the force between any pair of people in this classroom is pulling those people toward each other. Now, when we say force of gravity, we usually are applying the force of gravity of the Earth. And the force of gravity of the Earth is defined as down. That's how we define the direction, because we're being attracted toward the center of the Earth. We define the direction toward the center of the Earth as down. So gravitational force is an attractive force that's proportional to the product, that is the two masses multiplied together, product of the masses, and inversely proportional divided by the separation squared.
So next time someone says I'm too close to them, I'm just gonna say, well, it's gravity, not me.
Okay.
Tell me how that goes for you.
Yeah, if that works out, yeah. Okay, so that is our entire coverage of Chapter 4. Chapter 4 also deals with projectile motion, with what happens when I throw a ball, for instance. And we skipped over that for, we've got to get to things that I think are going to be more useful to you as teachers. So we're going into fluids now.
I'll be honest, I want to do kindergarten. Like, this isn't really.
I think it should be.
Think so?
Yes.
I'll get the metaphysics for them.
Density. What does density mean?
Yeah, thick.
Of a material of the same size.
When I hear of density, I think of thickness. Like a thick, foggy.
Like
Okay.
if my
Can't
water
see
bottle
through it.
was full, it'd be more dense than when it's empty.
You would be correct for the most part. If we consider the water ball as a single object, not as multiple objects, then yes. Density is a measurement of how much mass you have in a specified volume. So she used her water bottle. The water bottle has a certain volume it contains inside. And how much mass is inside divided by that volume gives you the density. Water is more dense than air, and so when it's full of water, the mass inside is more.
So G equals M over V.
So density, and we actually use a symbol, a Greek symbol.
Oh, well now I'm gone. There's no way. Oh god.
That's the Greek R, rho. Density is mass divided by volume, is what Jessica was saying, though. She's right. So something that's dense has more mass in the same volume. When you think of things that are dense, probably what comes to mind, once you know that definition, is lead. We think of lead as very dense.
My man's head.
I was waiting for somebody to say that when I asked the density, but you guys are all a little too respectful.
No, my man's head is dense too. He don't know nothing.
Okay.
That's actually quite intelligent.
Oh, I like
You're
Alex.
so nice. He knows that I make
Yeah, he's smarter than me for sure.
So
That was mom.
density is mass per volume, and we think of lead as very dense. And lead is very dense compared to something like water, which is dense compared to air. But there are other elements that are much more dense than lead. For instance, gold. Gold is very dense compared to lead.
I'm not sure how dense something is, but plopping it in water.
That works, because things that are more dense will sink, things that are less dense will float. So gold is extremely dense. Osmium and iridium, the two central things in the bottom of the main section of the periodic table, those are our most dense materials. And you see they're very close to gold, the properties clump.
Oh
I
yeah,
have to memorize the periodic table.
You will not have to memorize periodic table. When we get to chemistry, we'll learn about the periodic table. You'll have to know things like where the alkali earths are, where the alkali metals are, where the halogens are, where the noble gases are, where you have more electronegative molecule or atoms, excuse me. There's a lot of things you'll have to know about it, but you will not have to know, gallium is here on the periodic table. All right. So here's the equation the way Jessica would like it to be written always. In words. And I do understand there's a lot more comfort in words than there is in symbols. Why do we write stuff in symbols all the time?
We're lazy.
The two ladies are correct. Because it's faster and we want to use the fastest way possible, which can be translated as lazy. So the units. We've been learning units, and we learn things like what are the units for distance in the SI system? Meters. What are the units for time in the SI system? Seconds. What are the units for mass? This is the hardest one.
Joules.
Kilograms. Kilograms. The unit for force, Jessica. Newtons, which are kilograms times meters per second squared. The unit for energy, Alex. Joules, which is a newton times a meter or a kilogram times a meter squared per second squared. These units are important things. The units for density, because it's mass over volume, the unit for mass was kilogram. Volume is length times width times height, if you have a cube. And so if you have length times width times height, all of those have units of meters. So volume is meters cubed, meters times meters times meters. So density has units of kilograms per meter cubed as our standard SI unit.
Gross.
So this is,
That is disgusting.
I am sorry that it's disgusting to you. That's our standard unit.
Meters cubed.
But we very commonly use grams per centimeter cube. What's the difference in the two? 1 gram per centimeter cubed is equal to 1,000 kilograms per meter cubed, which happens to be the density of water. Water has a chemical formula, H2O, that you will learn as we get to chemistry. So if you use one unit or the other, it's very easy to translate between the two. It's just 1 gram per centimeter cubed is 1,000 kilograms per meter cubed. So the density of mercury is 13.6 grams per centimeter cubed, 13.6 times the density of water. So if I filled Jessica's bottle with water and then you weighed it, then we emptied it, we filled it with mercury instead, how would the mass or the weight change?
Well,
Mercury instead
it'd
of
be
water?
13.6 times heavier.
It'd be 13.6 times heavier, right?
And we'd have to go out for a water bottle.
Well, that too, but that's beside the point here. The point is to make sure we understand how that density works. Pressure. Pressure. How many people know? Dun 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 dun.
Yes. I listened to that one.
What song is that?
Under Pressure by Queen.
Not Ice Ice Baby
No.
by
What? They're totally different.
no. He just sampled Queen's song.
Oh, really?
Yeah.
They do sound similar. They do? I don't think so.
Anyhow, pressure is force per unit area. So pressure relates to force, but it's not the same thing as force. Now we talk about pressure, force per area. I have a certain weight. That's the force of gravity acting on me. Let us suppose that I take Jessica's photo. Actually, are you actually working on physics? No.
Yes.
Yes, I love that.
Yeah, I don't think so.
Yes.
So if I were to take Jessica's phone and stand on it It would be ridiculous. I wouldn't do that. All of my force would be on that area, right? And so we can take the force I'm applying and we can divide by that area, and that would give us the pressure I applied to it. Or, instead of Jessica's phone, I can take Annabelle's pen. If I step on Annabelle's pen, what would be the same?
Well, it would crack, yeah.
They would both crack, that is true.
But the pressure would still be the same.
The pressure would not be the same. The force I am applying would be the same, because it'd still be holding up my weight. The force would be the same, but this has an area that is, let's say, 1/10 the area of Jessica's phone. And if the area is 1/10 as big, then the pressure, the force divided by area, if you divide by 1/10, that's equivalent to multiplying by 10. So the pressure on the pin with me standing on would be 10 times greater than the pressure of me standing on Jessica's phone, even though it's the same force. Now, as you can see, the units, force, we've just gone through all this. Force has units of newtons. Area has units of meters times meters, which we more commonly call meters squared. And so the unit of force is a Newton per meter squared, which, to simplify life, we call a Pascal. Now that's the SI unit. When you put air in your car tire, you measure the pressure of the air. What unit do you use for the pressure of the air when you fill your car tire with air?
Wait, say that again?
What unit do you use for pressure, air pressure, when you fill your car tire with air?
Oh, they have that little thingy. And it's, I don't remember what it's called.
We usually say PSI. PSI stands for pounds per square inch. So PSI pounds per means divided by squared inch. So that's another unit, one that we're commonly using. Now, believe it or not, air is pushing down on you right now. You are indeed under pressure. The air is pushing on you with a pressure of about 14.7 psi. What does that mean if I tell you the air is pressing on you with a pressure of 14.7 psi?
It's pushing on us with an air squared. You can say it one more time.
What does it mean if I say that the air is pushing on you with a pressure of 14.7 psi?
So that means that the pressure of the air is pushing on us, the pounds of the air is pushing on us. No, the pressure of the air is pushing on us at 14.7.
Okay, 14.7.
Yeah.
What direction is the force? I haven't talked about this specifically. What direction is the force of air pressure?
No, well,
The net is downward.
would it be
But-
frontal?
It's always directed into the surface. So air is pushing down the top of my head, but it's
also-
pushing on, here that direction, here that direction.
So everywhere.
So it's everywhere pushing in. So air pressure is pushing me in everywhere. Now what about under my shoes? Is there air under my shoes?
Yeah.
You bet there is. If there wasn't, then the air pressure pushing down would be more than I could lift, and I'd be stuck. That's how suction cups work. You lower the pressure between the cup and whatever it's touching, and then the air pressure on the outside holds them together. So pressure, force per area, air pressure, 14.7 pounds per square inch, or we call that 1 atmosphere, by the way. (101.325) pascals. And that's where we will end for today. I'll see you again on Wednesday, when we will have yet another homework due. The homework is available to you, right?
Really gonna give us homework over Christmas or winter break?
I won't over Christmas break.
Okay, come on.
Oh, thank you so much.
But you're
Yeah.
giving us homework over winter break?
I believe so. I would have to.
My